Assalamu alaikum. In today's lecture we shall talk about working of a simple loop rotating in a magnetic field created by curved pole faces. The working of this simple loop will also explain some basic concepts which are involved in the working of real DC machines. This is not a real practical DC machine, however this is very useful to explain the basic concepts. Here we have north pole and south pole. The pole faces are not flat, rather these are curved. Inside these pole faces there is a cylindrical ferromagnetic material which can rotate inside these curved pole faces. On this ferromagnetic material we have a coil of wire, rectangular coil, which is placed on this cylindrical rotor. This rotating part in DC machines, that is called rotor, and the part which is stationary in electrical machines, that is called stator. This coil over here is a rectangular coil. If I see the front view of this setup, I have this situation. Here we have north pole and the south pole. Front view of this setup. These pole faces are not flat, rather these are curved. Inside these pole faces we have a cylindrical rotor. This rotor can rotate freely inside these poles, and on this rotor we have placed a coil of conductor, and if we look it from the front, we shall only see the front side of this coil, and these sides and the back sides will not be visible, so let's show them by small circles, the sides of the conductor. This coil is of this shape, rectangular shape, and let's also name these sides of the coil. This is side AB, and this side, let's name it side BC, and this side is CD. Here we know that flux lines always flow from the north pole to the south pole, and flux lines follow the shortest reluctance path. So here are flux lines which flow from the north pole to the south pole, and furthermore these flux lines follow the shortest reluctance path. So here, for example, this flux line will not follow this path, straight path, rather it will follow the path which has shortest reluctance. So shortest distance from reluctance of this ferromagnetic material and that of this core can be neglected. It is negligible. Mainly reluctance is due to this air gap, and the shortest path is from here. This one is the shortest path. That is the perpendicular distance from this curved pole to the curved surface of the rotor. That is the shortest path. Similarly, the flux lines over here, these will follow this path, and flux lines flowing from here will follow this path. So due to the curved pole faces, what we see is that these flux lines will always be perpendicular to the surface of rotor. We would like to derive an expression of voltage induced in this coil. This rotor is rotating, therefore this coil is also rotating. We already know that a conductor moving in a magnetic field, there is a voltage induced in it. So voltage will be induced in the this coil, and we want to derive an expression for the voltage induced in this coil. So let's discuss each side of the coil separately and derive an expression for voltage induced in each side of the coil. So let's first talk about this side, this side AB, which is indicated by a small circle over here. So this rotor is moving in counterclockwise direction. We know that when a conductor moves in a magnetic field, a voltage is induced, and that voltage is given by V cross B dot L, where V is the velocity of the conductor, B is the flux density vector, L is the length vector, as you already know. So this rotor is rotating with this angular velocity. What is linear velocity of this conductor? That is this side of the conductor. That is always perpendicular. So if this conductor is at this position, then this is the velocity of this conductor. And what is direction of flux density vector? Flux density vector is, this is the flux density vector, B. So V is perpendicular to B. So V cross B is simply V multiplied by B. What is direction of V cross B? Rotate first vector in the direction of second. V cross B is into the surface of board. So this is direction of V cross B, which is parallel to this conductor. Conductor is placed over here. So V cross B is also into the surface of board. Conductor is also into the surface of board. So V cross B, V is perpendicular to B, so V cross B is simply VB. Their cross product is parallel to L, so it is VBL. When conductor is at this location, magnitude of voltage induced is VBL. What is polarity of the induced voltage? Direction of V cross B is into the surface of board, and V cross B dot L is also into the surface of board. That is, the direction of induced voltage will be such that current will flow into the surface of board. So the current which is flowing into this conductor can be denoted by cross notation. So it is into surface of board. What will happen when this conductor will move slightly upward? So let's depict this situation over here. After certain time, this conductor would have moved to this location. So this situation is depicted over here. North pole, south pole. Flux lines always perpendicular to this surface. And now the conductor has moved to this location. This conductor has moved to this location. And its velocity, angular velocity, is in this direction. Linear velocity V is always tangent to this surface. So again, what is direction of V? This is direction of V, and this is direction of B. V is still perpendicular to B, so V cross B is simply V multiplied by B, and its direction is still into the surface of board. That is, direction of current can be denoted by this cross. So until this conductor is here, its voltage induced is given by the same expression. When this conductor moves to this point, after certain time, it would have moved to this point. Here, flux density is 0, and hence induced voltage will be equal to 0 when this conductor has moved to this position. So this induced voltage will be equal to V cross B into L until and unless this conductor is under the pole face, and it will become 0 when this conductor moves beyond the pole face. Why induced voltage is 0? Because flux density over here is 0. This conductor is beyond the pole faces, so influence of this magnet over here is negligible. Here flux density will be 0, and hence V cross B will be 0. Hence no voltage will be induced in the conductor, in this conductor, when it has moved to this location. So under the pole faces, this is the induced voltage. When the conductor moves beyond pole faces, that is induced voltage. This is voltage induced in conductor AB. Now let's talk about the voltage induced in the second segment, that is segment BC. What is voltage induced in segment BC of the coil? So let's see the direction. Again, this conductor V cross B is into the surface of board. And what is direction of L? Let's look at this diagram. V cross B is into the in this direction, into the surface of board. That is perpendicular to L. So induced voltage in segment BC, that is equal to 0. Why? Because V cross B is perpendicular to L. So dot product of two perpendicular vectors is 0. This conductor is lying like this one at the back end, and for this V cross B is into the board. So V cross B dot L, dot product of two perpendicular vectors is 0. Therefore voltage induced in segment BC, which is at the back end of this rotor, that is equal to 0. Similarly, we can determine voltage induced in segment CD. So if we have a look at this segment that is shown by a small circle over here, direction of velocity is downwards, B is towards right. So here this is direction of velocity, this is direction of flux density. What is direction of V cross B? Direction of V cross B, rotate V in the direction of B. So we have V cross B is out of the surface of board. And that is parallel to this conductor. This conductor, side CD, over here is like this one. So V cross B is parallel to this length vector. So V cross B dot L is simply equal to VBL, and its direction is out of the board. It can be denoted by dot notation over here. Again, this conductor, the same will be the situation until and unless this conductor is under pole face. This induced voltage will be equal to VBL. When it moves beyond pole face, then the induced voltage will be 0 when it is beyond pole faces. So under pole face. And what about voltage induced in this segment A, this segment and this segment? Again, by a similar discussion as that was carried out over here, the voltage induced in segment AD, that will also be equal to 0. What is total voltage that will be available over here? So what we see is voltage induced in this segment is such that the current flows in this direction, that is into the surface of board, and in this conductor it flows in this direction. That is the two voltage sources, this voltage source and this voltage source. These conductors now behave as voltage sources. So these are in series, and total voltage induced will be equal to the sum of two induced voltages. This voltage plus this voltage. So it will be 2VBL when conductors are under pole faces, and it will be equal to 0 when conductors are beyond pole faces. After a while, since this rotor is rotating, this conductor will move to this location. That is, it will become under this pole face. Likewise, this conductor, this side AB, which was under the influence of south pole, will now move to this location to become under the influence of north pole. That is, we will have this situation. This blue circle indicates this situation. That is, this is side AB and this is side CD. Now this conductor, since this rotor is rotating, this conductor has moved to this position. That is, now we have this conductor is CD and this conductor is AB. It is in a line like this one. We cannot show it on this two-dimensional figure, so only circle is shown to denote these conductors. So what will be the situation now? Now, if we look at the velocity and flux density vector for this conductor CD, so this is the situation: velocity vector and flux density vector. So now, what is the polarity of voltage induced? V cross V is into the surface of board. Now this is the situation. Previously, this was the polarity indicated by dot, and here it becomes cross. That is, previously this was the direction of current in this conductor. Now it is this direction. Similar will be the situation with conductor AB. Previously it was into the surface of board. Now it will be out of the surface of the board. That is, this will be the polarity of the induced voltage. That is, the current, if allowed to flow due to induced voltage, it will flow from B to A. So again, this voltage source and this voltage source, these are in series and add up. So total voltage is, again, magnitude of total voltage is again 2 VBL. What has changed is the polarity of the induced voltage that is available over here. Previously, the polarity was such that current was coming out of this wire, and now the polarity has reversed. It is entering into this wire and leaving this wire. So if we sketch the graph for induced voltage, that will look like this one. When conductors are under pole faces, induced voltage is 2 VBL, and when conductors move beyond pole faces, induced voltage becomes 0. After this situation, what happens is the polarity of induced voltage is reversed and it becomes minus 2 VBL. And then this cycle repeats itself, and what we see is that the voltage that is available over here, that is not a DC voltage. It is bidirectional. It is changing its polarity. For a certain time it remains constant. After that it becomes 0, and then it reverses its polarity to become constant again. It is not DC. How we can convert it into a unidirectional voltage? To convert this bidirectional voltage signal into a unidirectional voltage signal, we use an arrangement of slip rings, also called split rings. What we do is, we have this situation. We connect these wires with these split rings and place brushes over here. These brushes are in electrical contact with these split rings. What will happen with this arrangement? What we see is that, corresponding to this situation, what will be the case? This is side AB, this is AB, and this is side CB. What is polarity of the voltage? That will be over here. The current in this AB is into the surface of board, that is current will be flowing in this direction in the loop. We shall be having current coming out from this end. So therefore this is the polarity of the voltage induced over here during this half cycle. What will happen after 180-degree rotation of this rotor is that this side would have moved to this location, and the other side would have moved to the other location. That is, now here will be conductor A, B, and here will be conductor A, B, and here will be conductor CD. This will be conductor CD. And also the polarity of induced voltages would also have been reversed. But still what we can see is that the direction of current is still coming out from here. Although previously current was flowing from A to B, and now it is flowing from B to A, but still the direction of current that is flowing out of this wire is the same. That is, by using this arrangement, we shall have this kind of voltage signal. 0 when conductors are beyond pole faces, plus 2 VBL when conductors are under pole faces. It will again become 0 for a short time, and then it will again become 2 VBL. So by this split ring arrangement, we have converted this bidirectional voltage into a unidirectional voltage. It is still not a DC, it is fluctuating DC. We shall learn how we can get a pure DC or near DC signal from a DC machine. So the voltage induced in this machine is given by this expression. We can rewrite it in a form which is more convenient when we shall be talking about real DC machines. So let's do that. We know that the linear velocity is related to angular velocity by this relation. V is equal to R omega. And we also know that B is equal to flux multiplied by flux divided by perpendicular area. This is can also be written in this form: flux is equal to B multiplied by A. Remember that while using this relation, this area that has always to be taken as the area perpendicular to flux lines. So in this case, for the case of this cylindrical rotor, flux lines are like this one. Flux lines are like this one. So what is area which is perpendicular to these flux lines? So a situation is like this one. We have this cylindrical rotor, and flux lines are like this one. So what is the area which is perpendicular to these flux lines? The area is the surface area of this rotor. Total area of this surface area of this rotor is this total length. If I have this cylindrical surface, if I cut it open from here, the surface area, this total surface area, that is equal to this length multiplied by this length. That is this whole length, which is 2 pi r. 2 pi r is this length, and the depth, this length is 2 pi r, and this length over here is L. So this is total area, and half of it is perpendicular to these flux lines. So divided by 2. Total area divided by 2 is the area which is perpendicular to these flux lines. So to determine total flux is equal to total flux in the machine is flux density multiplied by the perpendicular area. Perpendicular area is total area of rotor divided by 2. By using this relation, this expression can be rewritten in this form: E induced, which is 2VBL when conductors are under pole faces. So what we notice is V is equal to R omega, 2R omega B multiplied by L. I multiply whole expression with pi and also divide it with pi. So this area, let's call it area per pole, because half of the area is under north pole and half is under south pole. So let's denote it area per pole. That is equal to pi r L. So r L multiplied by pi, that is area multiplied by flux density, that is the total flux in the machine. So this is 2 over pi flux into omega. B multiplied by all these constants, that is equal to flux. So voltage induced in the machine, in this simple DC machine, that is given by 2 over pi phi into omega when conductors are under pole faces. That is the voltage induced in this simple rotating loop depends upon the angular velocity of this rotor and the total flux in the machine, and also a constant. That is also the situation in real DC machines. In real DC machines, the total induced voltage also depends upon the speed of rotation of the rotor. It also depends upon the total flux in the machine, and it depends upon a constant which depends upon the construction of that particular machine. So in the next lecture we shall derive an expression for torque induced in this rotating loop.